Welcome to this Masterclass Explainer. Today, we are completely upgrading our theoretical intuition of fluid system design. If you're a practicing mechanical engineer or a student analyzing complex flow systems, you already know the deal. The fluids we actually work with in the real world, they rarely behave the way our basic textbooks suggest. So today we're diving deep into the actual mechanics of Maxwell fluids, unpacking the exact analytical solutions for oscillatory magneto-hydrodynamic flow. To kick things off, let's think about this. Why do those standard Newtonian fluid models fail us so drastically when we're trying to design things like modern polymer molds or magnetohydrodynamic (MHD) energy systems? Well, standard models just assume fluids respond instantly to stress, but in reality, that assumption causes highly unpredictable flow failures, especially during those volatile industrial startup phases. You see, the fluids we actually use in these high-stakes environments, they have memory. Okay, let's dive into the agenda for today. First, we'll go beyond simple Newtonian fluids. Then, we'll open up the Laplace Mathematical Toolkit. Next, we'll contrast transient versus steady responses, break down magnetic and porous forces, explore heat transfer and thermal dynamics, and finally, look at optimizing industrial fluid systems. Let's start with Section 1, Beyond Simple Newtonian Fluids. It is time to leave those perfectly simple fluid assumptions at the door and look at what actually flows through our industrial pipes. Just look at this direct comparison. On one side, the standard Newtonian Navier-Stokes equation relies completely on dynamic viscosity. But then, look at the Maxwell model. It brings in both fluid elasticity and what we call relaxation time. Essentially, the Maxwell model adds this absolutely crucial memory term to our equations. Yes, fluids hold a grudge. This means the fluid actively resists immediate deformation. It doesn't just flow, it behaves kind of like a memory foam mattress. It stretches, remembers its shape, and actually pushes back. Let's anchor this right into your daily reality. You guys aren't just dealing with water, right? As mechanical engineers, the materials you handle every single day require this complex understanding. We're talking about incredibly thick polymer melts being forced through extrusion molds, heavy lubrication oils under intense pressure in industrial engines, colloidal suspensions, and, even biological fluids like blood. These are classic non-Newtonian fluids where that elasticity fundamentally dictates the flow dynamics. Now, the defining parameter here in the Maxwell model is the viscoelastic relaxation time, which we denote as lambda-1. Think of a high relaxation time as a physical shock absorber embedded directly within the fluid flow. Higher values mean the fluid strongly opposes any time-varying deformation. In practical applications, like designing polymer cooling systems or optimizing industrial pipe flow, understanding this parameter is an absolute game changer because it suppresses momentum diffusion, which thins out the oscillatory boundary layer as the mold settles. All right, moving to Section 2, the Laplace Mathematical Toolkit. Let me put my professor hat on for just a minute here. Because to decode these dense, time-dependent oscillatory equations, we need a serious mathematical engine. Enter the Laplace transform. We all know dealing with partial differential equations can be a total nightmare, but the Laplace methodology makes it completely manageable. Step 1, we set up our dimensionless PDEs to generalize the model. Step 2, we apply the Laplace transform to move from the complex time domain over to the complex frequency domain, the S domain. Step 3, we solve those newly simplified algebraic equations. And finally, Step 4, we apply the inverse Laplace transform, relying heavily on the convolution theorem to pull our exact solutions right back into the time domain. This elegant transform is literally what prevents the rigorous math from becoming completely overwhelming. So the crucial point here is beautifully summarized by this quote from our source material. By ensuring the convergence of that Laplace integral, we aren't just getting close approximations. No, we are generating the exact analytical expressions for velocity, shear stress, and temperature. For precision engineering, having that exact analytical solution means you can model your entire system's behavior with absolute certainty. That brings us to Section 3, Transient versus Steady Responses. Let's look at the physical responses of the fluid itself. When we have an infinite vertical plate system that suddenly begins to oscillate, the fluid doesn't just instantly match that steady rhythm. Actually, there's a real battle going on between the transient flow and the steady-state flow. The transient flow is made up of these short-lived, decaying oscillations. This is exactly what happens during system startup. The fluid is kind of scrambling, trying to figure out what to do, which can cause some pretty dangerous pressure spikes. But as our mathematical breakdown shows, these transient startup spikes decay over time, eventually leaving just the steady-state, stable oscillatory motion to govern the long-term behavior. Notice how the chaotic effects eventually just vanish completely. Knowing the exact mathematical boundary where that transient flow dies out is huge. It allows you to predict exactly when an industrial system will stabilize after a perturbation. You can literally calculate the exact second your polymer mold flow or your heavy oil lubrication system will shift from a chaotic startup phase to a smooth, highly predictable operation.
Let's move to Section 4, Magnetic and Porous Forces. Now that we've got the timeline of the flow down, let's analyze the specific forces we can tune to actually control that steady-state flow, especially in magnetohydrodynamic devices.
Now, what's really interesting about this slide is how these distinct physical forces interact in a sort of tug-of-war. The Grashof number, which represents thermal buoyancy, fights to increase velocity rapidly. But then, look at the magnetic parameter and permeability. They introduce competing resistances. So buoyancy pushes the fluid along, while the magnetic field and the porous medium actively reshape how that momentum is distributed.
Let's zoom in on the magnetic parameter, M. In electrically conducting fluids, applying a magnetic field generates what we call a Lorentz force. This force acts directly opposite to the fluid's motion. Tuning this magnetic parameter is like having an invisible brake pedal. If your flow is too turbulent or it's moving way too quickly near the boundary, you can literally dial up the magnetic field to slow it down, all without ever physically touching the fluid.
Check out the drastic drop in magnitude here. As we increase that magnetic parameter from low to high, the fluid's velocity drops drastically. Those Lorentz forces severely damp the flow, which significantly thins out the momentum boundary layer. And this stabilization effect, it's absolutely highly desirable in complex MHD energy systems to prevent erratic shear stresses against your machinery walls.
On the flip side, we have the porous permeability parameter, K. If you increase the permeability of the medium the fluid is passing through, you reduce physical resistance. This allows the fluid to penetrate deeper and momentum to transport much more freely. Tuning this porous media resistance is an absolute must when you're designing filtration systems or trying to optimize energy extraction in practical porous MHD devices.
All right, Section 5, Heat Transfer and Thermodynamics. We've mastered the physical movement, so let's shift gears to thermodynamics. Let's look at how we manage cooling and how magnetic fields can actually improve heat transfer in specific energy systems. The big thermal knob we have here is the Prandtl number. This is the ratio of momentum diffusivity to thermal diffusivity. Basically, a higher Prandtl value means heat diffuses way slower than physical momentum. Because the heat can't escape quickly, it gets trapped close to the wall, creating a remarkably thin thermal boundary layer. But here is the cool part. By applying those magnetic fields we just discussed, you can actually thin this boundary layer further and drastically improve the heat transfer away from sensitive machinery. 0. That's exactly what the velocity smoothly decays to as you move away from our oscillating vertical plate. This mathematical 0 proves something absolutely vital for design engineers. The intense effects of thermal buoyancy and heat transfer we've been talking about, they are highly localized to the near wall region. The chaos is all at the boundary, the deep fluid remains totally unaffected.
Finally, Section 6, Optimizing Industrial Fluid Systems. Let's take all this brilliant math and theory and bring it right back to the practical, everyday work of a mechanical design engineer.
And this right here brilliantly illustrates why we spent time on those Laplace transforms earlier. Decoding these specific variables gives you, the engineer, direct control over the system design. You can tune the relaxation time for perfectly predictable polymer mold flows. You can adjust the magnetic fields to stabilize MHD generators. You can balance Prandtl numbers for optimal active cooling. And you can utilize porous media permeability for incredibly precise lubrication control. To really cement this masterclass, I want to leave you with this fundamental conclusion. The interactive forces of buoyancy, porous medium interaction, magnetic field, and thermal transport determine the oscillatory velocity field in the boundary layer. The takeaway? You are not a victim of unpredictable non-Newtonian flow. By balancing these exact forces, you completely master the fluid's behavior. You now possess the exact analytical solutions and the theoretical intuition behind them. So the question I'll leave you with is this: how are you going to tune the magnetic and thermal parameters in your next fluid system design? Thanks so much for joining me for this explainer. I really hope you're eager to take these exact equations and apply them directly to your own engineering schematics. See you next time.